actually I'm going to change this to that number. So it's a change this to plus, 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 and a plus, and a plus. So it's simply change to that. Change plus. Just to make things easy. I don't want to make it too complicated. It's already complicated. So now what we can do, we're gonna kind of clear the terms. So you can see this is 1 plus 1 s plus half squared minus. So what is this is a shin function. This is shin. We know that that's a form of a hyperbolic sign. So what is missing is square root 5 over 2. So we're gonna multiply and divide by that. So it's a 4. So we are missing square root 5 over 2. So we're gonna divide and multiply. Good. So yeah, I didn't write it properly. So what we're gonna do, so we can write this one as s plus 1/2 squared minus 5/4. So square root 5 over 2 is missing, and then we multiply outside upside down of that. That's what we do. And then we have also e to the minus 3s term. So this is simply the hyperbolic sign, and then we're gonna do the shifting part. So that means the final answer. So we can see. So this simply corresponds to e to the negative 1/2 t shin square root 5 over 2t. So that's the function coming from there that you know already. Now what we can do, we can use the e to the minus 3s to add a switch here. So taking inverse Laplace transform, taking inverse Laplace. So what we have is xt equal 2 square root 5 ut minus 3 ut minus 3 e to the minus 1/2 t. So what we're gonna do, what's gonna happen, you have to shift by minus 3, so t minus 3 comes there, and then shin square root 5 over 2, this one also t minus 3. This is because of the e term. This is coming from the e term. Good. So that is the answer for this problem. So you can see that it suddenly start at after 3. Then that's when the impulse. So I mean, you can see this. That's the whole problem. So this is like a kind of simple problem compared to other problems. Okay. Good. So that is the end of Laplace transform method. Next, we're gonna do. We can learn how to solve systems. So we can talk about some examples there. In this, we're gonna talk about how to solve system of equations, system of ODEs in this case. So we can talk about 3 methods. The first one is the elimination method. Method. So there are 2 types of problems that we can try. So there are 2 types. We're gonna go one by one. And then the next one is the Laplace transform method. Laplace transform method. So this is actually kind of sophisticated because you can handle a lot of cases with that. And then the third one is the eigenvector method. Eigenvector method. So under the eigenvector method, we're going to consider 2 cases. We can do 2 by 2. 2 by 2 case is very easy. And then we can do 3 by 3. When you do 3 by 3, there are actually 3 cases to consider. One is there are 2 eigenvalue case. That's kind of easy. Very easy to find eigenvectors. We can use shortcut for that. So we will use the shortcut. And then there are 3 eigenvalue case, 3 eigenvalues. uh, 3 eigenvalues. In that case, what we normally do, we use the eigenmatrices for that. Eigenmatrices. That's the new concept. We discussed that earlier in a different video, so you can look at that. And then there's a case also what we call defective matrices, and we are not going to discuss that in this, but we have that in another video. So the defective matrix, but we will not discuss that here. So we gonna discuss one from 2 by 2 and one from 3 by 3 with 2 eigenvalues. So that's what we can do. Okay, so let's start one by one. Let's do the elimination first. So the elimination method. Elimination method. So there are two types. So let's start with type 1. So let's do that with the problem. So let's say solve the system. So let's say 3 dx over dt minus dy over dt, and on the other side you're going to see some function of the independent variable. So let's say just put something. So like let's say sine t, and then we have another one dx over dt plus 2 times dy over dt, which is equals to 2e minus t minus 3 let's say cosine 3t plus 1. So what we can do, we're going to call this equation 1 and equation 2 for references. So this is like just like how we do this, like as like when we solve linear systems, like when you have like with several variables, if you see like linear systems, we know how to do. We can just eliminate one variable. So we can use the same argument. For example, in this case, you can see when you see plus and minus sign, that's the kind of we're gonna pay attention to, because that's gonna make it easy. So what we're trying to do is, so in theory, what we do, eliminate one of the x prime or y prime. So that's the kind of goal. So eliminate one of x prime or y prime. For example, when you see plus minus sign, that's we're gonna pay attention to that. For example, if you multiply the first equation by 2 and add it to the second one, you can see the dy term gonna go like eliminated. So that's what we're trying to do. So we can see by 2 times the equation 1 plus 2. If you do that, if you multiply the first equation by 2 and add it to the second equation, you can see dy term get cancelled. So you're gonna get 2 times 3, that means 6, plus 1, so you get 7 dx over dt equal. So you multiply the first one by 2, so that means 2t squared minus. Okay, let's look at what's going to happen here. So we're going to multiply this one by 2, so you get negative 16, and you add, there are in the second equation you also have 2, that means you end up with 14 e to the negative t, and then we have 2 sine t you're going to get. In the bottom you're going to get 3 cosine 3t and then plus 1. So that's what you get. Just a long expression because there are many terms. Just integrate now. Once you integrate, you get x. So x equal the integral of dx over dt. Actually, before we do that, we're gonna divide this. Yeah, let's try that instead. So dx over dt, if you divide by 7, you can see it is 7. It is 2 over 7. 2 over 7 t squared minus 2 e negative t plus 2 7 sine t minus 3 7 cosine 3t plus 1 over 7. So that's what you get. Now what we can do, we're going to integrate the two sides. So just integrate with respect to t, you get x. Okay, so now what we can do, integrate. So once you integrate, you get x, which is the integral of dx over dt from calc 1. Uh, so just integrate. So we have a lot of terms, so integrate term by term. So we have 2 over 7 t squared. I'm going to write everything, but you can skip this step. It's not really necessary. So it's negative 2 e to the negative t plus 2 over 7 sine t minus 3 over 7 cosine 3t plus 1 over 7 dt. So if you integrate, I'm going to write the answer here. So you're going to get, you have to divide by 3. So it is 2 over 21 t cube minus, okay, when you have exponential function, you divide by the constant. So it's negative 1. So that means it's going to be positive 2 e to the negative t. Sine means negative cosine. So it is negative 2 over 7 cosine t. In the next one, this is a cosine, but there's a 3. That means you have to divide by 3. It's a cosine, you can sine, so it's a negative 1/7 sine 3t because you divide by 3 plus 1 over 7t plus c1. You introduce a constant name. So that is the solution for x. Now what we can do, there are two ways to do, two ways to find y. One way is you can plug in this solution in one of those equations. So if you plug in that solution in one of those equations, you can see that the dx over dt can go away. And then you only have dy over dt, then you integrate that to find y. The other way is just do the same thing as we did before to eliminate the x term, dx over dt term. And then you're going to get dy dt and just do the same thing. So, so I'm going to write this, find dy over dt as before. There are two ways to do it. Okay, so we can use one of the methods. So we can do by 1 minus 3 times 2. Because why we do that? Then you can, because you have a 3 and a 1. So if you multiply the bottom one by negative 3 and add, dx over dt gonna go away. So that's exactly, so we're gonna get negative 7 because you multiply the top one by bottom one by 3. So you get negative 6, and there's another one, so you get negative 7 dy over dt, and then you're gonna get t squared minus 14 e to the negative t plus sine t minus 9 over 7 cosine 3t minus 3. That's what you get. Good. And then what we're going to divide by 7 as before. So you get dy over dt equals negative 1 over 7 t squared positive 2 e to the negative t negative 1 over 7 sine t, and then yeah, it's again negative negative 9 over actually so yeah, so there's a, I don't know whether it's negative 7 9 or 7, it's just 9. So you have plus 9 here because we multiply, so let's look at that one again. So we have, yeah, so we can multiply the bottom by negative 3, so it becomes positive 9. I don't know why you're right there. Positive 9. Now here is going to be negative 9 over 7 cosine 3t, and then we divide by negative 7, so it's going to be positive 3 over 7. So that's what we have. And then integrate. Okay, so integrate. So once you integrate, you're going to get the answer. So y equal the integral of y prime dt. So just integrate. So you get negative 1 over 21 t cube, negative 2 e to the negative t, and then sine means negative cosine. So it's been 1 over 7 cosine t, and then negative you divide by 3. So we get 3 over 7 sine 3t plus 3 over 7, you add another constant C2 for that. So those are the two answers. So we have the X and the Y. So you can see it's just very direct way to simplify that. So that's a type 1. So let's talk about the type 2. So what is type 2? So type 2. Um, Type 2, like the situation there, we cannot do this. Okay, so let's look at the problem again. So let's say solve the system. Solve the system. Let's say x prime equal 3y, y prime equal 2x minus y plus 3. So that's a system. Sometimes we write the curly brace like that. It's not really necessary. We're going to call the equations 1 and equation 2. Now you can see there's no way you can just solve for 1 here because there are no other derivatives. So that means the method that we used for the previous one doesn't work here. So what you're going to do is you're going to take derivatives. We can take derivatives and then try to substitute from the other one to remove one variable. Now you have two options. You can take the derivative of the first one or take the derivative of the second one. But you can see the 3 here. Since we have the 3 here, to avoid undetermined coefficient method, we can take the derivative of the bottom one. Then that's 3 gonna go away. So that's the trick we use here, because if you take the derivative of the top one, you end up with the equation which is undetermined. You have to use the undetermined coefficient method, so that's gonna be a little difficult. So we can avoid that. Take the derivative of the bottom one. Okay, so we have to think sometimes. So take the derivative of the second equation. So the answer, taking the derivative, taking the derivative of equation number 2. So you're gonna get y double prime equal 2x prime minus y prime, and then plus 0. That's gonna go away. Now what we're gonna substitute for x prime. Okay, so substitute substitute for, let's say substitute for x prime. So if you do that, you get y double prime equal 2 times, what is x prime? X prime is 3y from the first equation, minus y prime. Now what we can do, we can bring everything to one side. So it is y double prime plus y prime minus 6y equals 0. This is a simple constant coefficient differential equation, and we write the characteristic equation for that. So the characteristic equation is lambda squared plus lambda minus 6 equals 0, and which has factors lambda plus 3 and lambda minus 2 equals 0. This is gonna say that lambda equal negative 3 and 2, so that means you can write the solution. Okay, so the y is simply using the formula. So y is simply c1 e to the negative 3t plus c2 e to the 2t. So that is the y. Now what we can do in this problem, since we know y, you can, because the goal is to find x. So what we can do is you can plug in that to one of those equations wherever you see y, and then solve for x. So you can see that you can do that in two different ways. The one is you can just substitute for, take the derivative, because we already know what is the derivative y prime, and then we can substitute that, take the derivative and plug into the equation number 2, then you get x. Or substitute in the 1. In the 1, we know that this y value, substitute there and then integrate again. So we can use that one because that looks little simple. So by 1, we're gonna say x prime equal 3y. So now just plug in for y. So it is 3 times c1 e to the negative 3t plus 3 times c2 e to the 2t. Now what we do? Integrate. Okay, so integrate. So you're going to get x, which is the integral of x prime dt. Just integrate the terms. So that means you can divide by negative 3. So you're going to get, let's write 3c1 times e to the negative 3t. So this step is not really necessary, you can just write the answer directly. And then here the same thing, so 3c2 e to the 2t divided by 2. Now there is a question whether we are going to add another constant, and you can see that this is we have two first order equations. That means you only need two constants. We already have the constants, so that means we are not going to add anything new. Okay, we are not going to add c3 here, so I'm going to write, but I'm going to say we are not going to do that, okay, because we already have two constants. So that's the reason we have c1 and c2. We only need two constants. Good. And then we can simplify if you want. So that means the final answer gonna be negative c1 e to the negative 3t plus 3 halves c2 e to the 2t. Yeah, that's how we do it. So you can see it's not that difficult, but you have to kind of think before jump, okay? Because which one you take the derivative depend. So you know, can give you like a different answer. I mean, it can be a little lengthy if you take the derivative of the first one, because you have to solve undetermined coefficient problem. Okay, but if you take the derivative of the bottom one, is much easier. So it's always depend on the problem. You cannot say beforehand what's going to happen. Okay, let's go to the next type, next topic, the Laplace transform method. So Laplace transform method. So what we can do, let's again look at a problem. So what we normally do is, so let's discuss the argument. So we can take the Laplace transform of the equation. So because you can see it's a system now, so you can see many equations. So we take the Laplace transform of all the equations. So take Laplace transform of the equations instead of one equation, and solve. And so after you get the equations, you're going to see a system with those x's, y's, things like that. So we're going to solve for them as we did before, okay? And solve for x's, y's, like that, because we don't know how many we have. So solve for them using the elimination method. So you can see, yeah, let's write it. I'm going to say fill up using elimination. Then take the inverse Laplace to find xt, yt, like that. So it's a very simple idea. Take the Laplace transform. So you get a system. In that system, you can see it is just there are no derivatives. You just use the elimination to find them, and then take the inverse Laplace. So yeah, so take the Laplace transform, eliminate, and then take the inverse Laplace transform. Those are the steps. So let's just do one problem, but I'm not going to completely solve the problem because those going to be a little lengthy. I'm going to show you the steps, and then you can finish this. So let's do this problem. So example, solve the system. Let's say d squared x over dt squared plus 3x minus y equals something. And then let's say we have dy over dt. So this is the interesting part. You can have anything here, not like before. So it is negative 4x plus 2y, some numbers, and then 3e negative t. With the one of the problem here, you need to give the initial conditions, because otherwise you can solve. So let's say x0, y, x0, x prime 0, and y0, all of them are 0, just to make it a little bit easier. Okay, so that's the problem. Now what we can do, take the Laplace transform of those two equations. Okay, so answer, taking Laplace transform, we can have, in the first one we can have s squared xs plus 3xs minus ys equal, what's the Laplace transform for? 4 over s. So we get that equation. And you can see that just xs, there are no derivatives, no other powers. From the second one, you're going to get s, ys minus 4xs plus 2ys equal 3. This is the eat function, so it is s plus 1. Those are two equations that we get. So we can isolate the sx term as a factor. So, and then you can also combine these two. So let's do that. So if you combine them, okay, so combining, let's say combining, we have s squared plus 3sx minus ys equal 4 over s. In the other one, you can see negative for sx. It's a good idea to write sx first and then yx next so that you see the pattern. The other one, you're going to see s plus 2. Yeah, I'm going to write this a little closer to that. So it is plus s plus 2 ys equal 3 over s plus 1. I'm going to call this equation 1. I'm going to call this equation 2. Now think of how to eliminate one of the variables. So for example, you can see, let's try to eliminate the ys. If you want to eliminate ys, think of this term because that's the coefficient. So what we're going to do, we're going to match the coefficient with the opposite sign. So for example, if you multiply the first equation by s plus 2, the whole equation by s plus 2 and add it to the second equation, the ys term gets away. It's going to go away. Okay, if you multiply the first equation by s plus 2 and add it to the second equation, the ys term going to go away, so you can solve for sx. So that's the whole point. So let's do it. So by we can do s plus 2 times equation 1 plus 2. If you do that, you can see the ys term has the same coefficient, so when you add them, same and opposite coefficient, so when you add them, they're going to cancel out. So you simply have s plus 2 times s squared plus 3 minus 4 from the bottom one times sx. That's what you have. On the other side, you have 4 times s plus 2 over s plus 3 times s plus 1. That's what you get. So if you want, you can simplify this in to get one expression or leave as two. So it's how you want to do it. Now you notice something. You can see that if you simplify the what is in the bracket, you get s3 plus 2s squared plus 3s plus 2, and then which has factors s plus 1 and s squared plus s plus 2. And if you don't know how to do this, look at the other video about factoring polynomials, so that explain how to find factors like this. So now what we can do, we can divide both sides by that. So you're going to get sx. So let's divide both sides. So we have I mean, if you had s plus 2 here, then you can cancel, but it doesn't happen like that. So we get 4 4s plus 8 divided by s plus 1 s squared plus s plus 2, and also we have extra s in front, and plus 3. What's going to happen here? You have s plus 1 already, so it is s plus 2 squared s squared plus s plus 2. Now what we want to do is just invert. So use the try to find factors, the partial fractions, and invert. So you can do either that way, or also you can use the convolution if you want to find inverse. So whatever the method that you use, what you want to do now is the inverting, but I will not do that. I will say, okay, so invert to find xt. And then what you do, you can plug in this xt in one of those equations and solve for ys, or do the same thing as before, try to eliminate the sx term by just switching the variables and multiplying the opposite one and adding. So you can use one of those methods to solve for yx and xt. Okay, and then you can say so you can do an invert. Okay, and then the next one is find ys similarly. Um, to do that, uh, substitute xs, because we already know sx in 2, and we can say solve for ys and invert. This is just one way to do it. The other way is just do the elimination as before and solve for y. So it's sometimes, I mean, it depends on what we have. Or use elimination to find ys. So you have two ways to do it. Either you substitute into the other one, because we already know ys, we already know sx, and solve for ys, or just use the elimination to find ys. So you know, it depends. Okay, so that's how you finish the problem. So I'm not going to do it because it can take too much time, but this is the way to do it, because this is very useful when you have like a large system. So Laplace transform method can help you to find the solution. So we know the method. So let's move on to the last one, that is the eigen vector method. So let's talk about that. So eigenvector method, eigenvector, or you can say eigenvalue method. Okay, eigenvector method. So let's talk about the steps. So we're gonna go with the first step. What we're gonna do, we're gonna write the system using a matrix form. So write the system, in write the system in matrix form. That means x prime equal ax form. That's the first step. And then what we can do, find the eigenvalues. Find eigenvalues lambda I of a. That's the second step. The third step is use any method. So you can either use a shortcut that we discussed earlier. So there are several videos for that, for the 2x2 case and 3x3 case. So use the shortcut or the regular method, the Gauss elimination method. Okay, the shortcut or the regular method to find the corresponding eigenvectors, So you can do the shortcut or the regular method. Shortcut is really short. Okay, so and then let's say vi, eigenvectors vi is the corresponding vector, and then we write the solution. So write the solution. So we know that the solution is xt, which is given by c1, the v1 e lambda 1 t. So the v1 is the corresponding eigenvector of lambda 1, and then just like that. So we're gonna go v2 e lambda 2 t. So like that. So there are n many. So it is cn vn e lambda n t. So there are so not. So lambda i's may be equal, but the vi's v1 v2 vn should be linearly independent. So that's the only requirement we need. Those eigenvectors has to be linearly independent. But there's a fact, this we discussed earlier, the eigenvectors of different eigenvalues are linearly independent always. So eigenvectors of different eigenvalues are linearly independent. That you can show. That's the case. They are linearly independent. But sometimes what happens, even if you have some repeated eigen values, you can show that those vectors are linearly independent. In that case, you can still write the solution in this form. Okay, so we can use this form for two cases: the distinct eigenvalues or repeated eigenvalues, but with linearly independent eigenvectors. Okay, so those are the two cases: one with distinct eigenvalues or one with some equal eigenvalues, repeated eigenvalues, but with linearly independent eigenvectors. So if you want, we can like kind of repeat that because that's a kind of important step. Uh, so we use this form. Of the solution when for distinct eigenvalues, or some repeated eigenvalues, with linearly independent eigenvectors v1 v2 through vn. So for those two cases we can use this form of the solution. So some repeated eigenvalues with linearly independent, this is important one, linearly independent eigenvectors. Okay, so let's try to do two examples, one from 2 by 2 and another from 3 by 3. So let's start with the 2 by 2 one. So so example 1. So let's say use eigenvector method to solve the system. Let's say we have x prime equal 3x plus 4, 3x plus, let's say 3x plus y, and then y prime equal 2x plus 4y. So that's the system. So we can do this using the type 2 elimination method. You can take the derivative and plug in from the other one. You can do that and then eliminate one of the variable. Let's see how to use the eigenvector method. So the answer. So we're gonna let x, which is the vector of x and y, those are the solutions. Then we know that x prime is simply x prime y prime. So we can write the system in this form. So so write the system in matrix form. So the next one is write. So I'm gonna write the steps, but you don't want to do that. I mean, it's just guiding you. But in the exam, you don't write those things. So write the system. I mean, you can to make it like more logical. So write the system in matrix form. So we have x prime, the coefficients 3, 1, 2, 4. So those are the coefficients times x. So we just put the coefficient and put x there. Now what we do, we're going to find the eigenvalues. Okay, so we're going to, so this is A. So I'm going to call this is A. So we're going to find the eigenvalues of. So next step, find eigenvalues of A. For that, we can look at the determinant of A minus lambda I. So that is the, you subtract the lambda from the diagonal entry. So it is 3 minus lambda, 1, 2, 4 minus lambda. So this is simple. So this is a 2 by 2. So we're going to multiply the diagonal first. So multiply the diagonal and subtract the other diagonal. So minus other diagonal means 2. You set this equal to 0. And you can see that this simplifies to lambda squared minus 7 lambda plus 10 equals 0. This has factors lambda minus 2 and lambda minus 5 equals 0. This implies that lambda equal 2 and 5. So those are the eigenvalues. Okay. So the eigenvalues are lambda equal to and 5. Now what we can do, we're going to find the corresponding eigenvectors. So find eigenvectors. Find eigenvectors. For that we can use a shortcut method. That means eigenvectors are simply the columns of the complementary eigenmatrix, the other eigenmatrix. So remember, the eigenvectors are the columns of non-zero columns of the other eigenmatrix. So we're going to do that. So for lambda equal 2, we're going to calculate the kappa matrix of 5 because that's the other eigenvalue. So that means you subtract 5 from the diagonal, 3 minus 5, 1, 2, 4 minus 5. So you're going to get the columns as negative 2, 2, 1, negative 1. These are the eigenvectors. And you see that they are just a multiple of each other. So that's the eigenvector. So that means this implies that eigenvector for lambda equal 2 are the column. Just pick any column or any multiple. So 1, negative 1. That's the eigenvector. Okay. So you simply pick one of them or even a scale version of that. So I pick that one. Or you can pick the other one, or you can even multiply by something. Now what we're going to do, we can do the same thing with the other eigenvalues. So for lambda equal 5, now we're going to calculate the other one. So we're going to use 2 here now. So if you use 2, subtract 2. So it is 3 minus 2 and 2, 1, 4 minus 2. So you're going to get 1, 2, 1, 2. So you can see they are the same, and that's the eigenvector for lambda 5. So which is as eigenvector for lambda equal 5. So which is 1, 2. So we found the eigenvectors. Now what we can do, just use the formula. Okay, so very simple. So the formula. So now write the solution. So we can write the solution. So which is xt equals c1 v e lambda 1 t plus c2 v2 e lambda 2 t. So that means c1 eigenvector of 2 is 1, negative 1. So e2t plus c2 eigenvector of 5 is 1, 2. So it is e to the 5t. So that's the solution. Also, you can simplify if you want, but that's not necessary. I'm just going to write it in a you may simplify. But that's not necessary. So let's say how to simplify this one. Then you can write xt. So what we're going to distribute this. So that means you can first say C1 negative C1 times e to the 2t, and if you multiply by C2, it is C2 2C2 e to the 5t. Now we're gonna multiply inside and add. So that means if you multiply inside and add, you're gonna get C1 e to the 2t from the first one. From the second one, it is C2 e to the 5t. And here also it is negative C1 e to the 2t plus 2c2 e to the 5t. That means those are the two solutions. So, so therefore, you can say the x solution, that's the first component, which is c1 e to the 2t plus c2 e to the 5t, and the yt, that's the second component. That's how we define the x. So actually this is not simple x, this is the vector x. So this is the big vector. That's a vector solution. Yeah, even here. So that's the vector solution. Good. So it is, and then we have c1 e to the 2t plus 2c2 e to the 5t. So that's the solution. So you can write it like that, or you can just leave the first version. That's fine. Good. So that's how we solve the system of 2 by 2. Now let's try to do one from 3 by 3. So let's solve this one. So example, yeah, actually to be better, we're gonna put everything in one side. Okay, and then one more thing, if this is just a note, if initial conditions are given, we can find C1 and C2, because if you know the initial conditions, just plug in them here and solve for C1 and C2. So it's a simple task. Okay, so let's do the 3 by 3 now. So the 3 by 3, let's do just one example, just to recall what we did. But there are like 4 examples solved in the main lecture. So you can look at them if you need more examples. So let's say solve the solve the system of ODEs. So it is dx over dt equal 3x minus y minus z dy over dt, which is x plus y minus z dz over dt, which is x minus y plus z. So what we can do, we can write the system in the matrix form. That's the first step. So the answer, if it is not in the matrix form, write in a matrix form. So so we're going to define the x vector, which has 3 components, x, y, and z. Now what we're going to writing the system in matrix form. Okay, writing the system in matrix form. So we have x prime equal the coefficients 3, negative 1, negative 1, 1, 1, negative 1, 1, negative 1, 1 times x. So that's the system matrix A. Now what we can do, we can find the eigenvalues first. Okay, so find the eigenvalues. So the 0 equal the determinant of A minus lambda I. So that means you subtract the lambda from the diagonal entry. So 3 minus lambda, 1, 1, negative 1, 1 minus lambda, negative 1, and then negative 1, negative 1, 1 minus lambda. So that's what you get. So you can use the Laplace expansion or the cofactor expansion to find the get the equation, but sometimes it may be a good idea to use the determinant properties to simplify this first. Like, try to get like more zeros. You can see they are 1 1, they are equal. So if you subtract them, that means if you add the negative 1 of the other row, you get a 0. So it's always a good idea to get extra zeros, then it's the calculation going to be easier. So we can do that. So the first thing we're going to do is we notice that there's a 0 here, there's a they are equal, so we're going to get a 0. So we're going to subtract. So what we're going to do is I'm going to subtract, I'm going to add the negative 1 of row 2 to row 1. So let's do that. So if you do that, so that means you subtract row 2 from row 1. So you get 2 minus lambda, and you get lambda minus 2. So they are equal, just opposite sign, and this is 0. So that means you can take the lambda minus 2 as a factor. So that's a good thing. And then here we have 1, and then 1 minus lambda, negative 1, 1, negative 1, 1 minus lambda. So how we did, what we did, we went R1 minus R2. Now what we can do is we can pull the lambda minus 2 out as a factor. So if you do that, it is lambda minus 2 as a factor from the first row. So you get minus 1 and then 1, 1, 1, 1 minus lambda minus 1. So we have a 0 here, minus 1, 1 minus lambda. Now what we can do is you can add row 1 or column 1 to column 2 to get another 0. So let's do that. So we're gonna do that. So we're gonna get one more 0 by doing so. I mean, you don't have to do that, but this is gonna make the calculation much easier because it's easy to find the factor. So what we're gonna do, we're gonna add column 1 to column 2. So it is negative 1, 1, 1. You get another 0 and 1 minus lambda. No, it's 2 minus lambda because you add that. So this is going to be 2 minus lambda. You add column 1 to column 2. So this becomes 2 minus lambda. This is 0. And then 0 minus 1, 1 minus lambda. So what we did, we add column 1 to column 2. Good. Now we can write the expansion. So once you write the expansion, you can expand at this point, and you can see you only have one term you get. So that means if you write the expansion now, you're going to get it's a negative because negative 1 times lambda minus 2, the 2 by 2 determinant, which is 2 minus 0 minus 1. There's a 0 here, 1 minus lambda. So that means you already get the factored version. So negative lambda minus 2, 2 minus lambda, 1 minus lambda. Okay. So this is simply, if you switch a term, this is lambda minus 2 squared, 1 minus lambda. If you set this equal to 0, this says that lambda equal 1 and 2, 2. So that's a repetition. So that means there are only 2 eigenvalues. So this is an easy case because there are only 2 eigenvalues. What we normally do, we're gonna find the so let's write that 2 eigenvalues because that's exaggeration. 2 eigenvalues. So what we normally do when you have 2 eigenvalues, we're going to multiply the corresponding eigenmatrices. So the find the eigenvectors, find eigenvectors. So what we do, since there are only 2 eigenvalues, we're going to use eigenmatrices. So we can use eigenmatrices for that. So what you're going to get is, so we're going to do the eigenmatrix product. So it's one eigenvalue is 1 of A times the other. So we just get the 2 kappa matrices and we're going to multiply them. So let's do that. So what is the first eigenvalue? Is 1. So we're going to subtract 1 from the diagonal. So you're going to get 2, 1, 1. And then negative 1, you subtract 1, so you get 0, negative 1, and then negative 1, negative 1, and 0. That's the first one. The second one is you're going to subtract 2 from the diagonal. So you get 1, 1, 1, negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Now what we can do, we're going to multiply. We're going to multiply and see what you get. If you get 0, you're lucky. The columns are eigen vectors. So you can see that for example, if you multiply this row with this column, you're going to get 0. You got 2 minus 1 minus 1, so 0, and you can see that everything is 0. Okay, very good. That means the columns are the eigenvectors of the other eigenvalue. Okay, so that means so these columns, there are 3 columns here. These columns are the eigen vectors of lambda equal 2, and these are the eigenvectors of lambda equal 1. So it's always the opposite one. Good. So let's try the eigenvectors. Uh, so the eigenvectors are for V lambda 1, you can see they are all the same, so it is 1 1 1, or just a multiple of that. So you can see that's exactly, you see that there. And for lambda equal 2, we need 2 eigenvectors. Just pick any column you like, so any column, or even any linear combination or rescaling. For example, I can divide the second column by -1, so you get 1 0 1. And then if you divide the third column by -1, you get 1 1 0. Also, there are more things. For example, if you add the column 1 to column 2, you're gonna get 1 1. So that's another one. So you can do a lot of other things. So you can just add them. You can multiply by one something and add them. Okay, just any column operation. So, but we need only 3. So, and then you can also see that those 3 are linearly independent. Okay, so they are linearly independent just by observation, because where the 0 is. Because when you have a 0 like that, it has to be linearly independent. Okay, so they are linearly independent. Since they are linearly independent, you can have the solution. So the solution vector xt, which is simply c1 v1 e lambda 1 t, c2 v2 e lambda 2 t, c3 v3 e lambda 3t. So if you substitute, you're going to get c1 times the first one 1 1 1 e to the lambda, what's the lambda value, is 1, so it's t. And the second one is c2 times 1 0 1, the lambda value is 2t. The third one is c3, the eigenvector is 1 1 0 e to the 2t. So that is the solution of the system. As before, we can, if you want, you can just multiply through and add them and then get 3 equations, but that's not necessary. But this is a solution. Yeah, c1, c2 and c3 are constants. So you can see it's not that difficult, it's very simple. But this is for 2 eigenvalues. If there are 3 eigenvalues, what we normally do is we're gonna pick, like if you need the eigenvector for lambda 1, what we can do, we're gonna pick the other 2 eigenmatrices and just multiply them, but we only need one column multiplied by the other matrix. So it's very easy. You can get the answer really fast. You only pick one column, normally with many zeros. So we can multiply that with the other eigenmatrix, so you get the eigenvector. Just keep doing it for other ones. So you pick the other 2 matrices, pick a column, multiply by the other matrix, you get the eigenvector. So just simple multiplication. So that's the end of this review.